Welcome to the deep dive. We're jumping straight into machine learning today.
Hmm.
Think about it. It's the engine behind so much now, right? Recommendation science.
Absolutely. It's
Yeah.
all about computers spotting patterns, really.
Yeah.
Patterns hidden in just, well, mountains of data.
Which is becoming so crucial everywhere.
Exactly. And this deep dive, we've designed it for you, the listener, someone looking for a clear, solid understanding of the key ideas in ML.
Without getting totally swamped in jargon.
Precisely. We've looked at, beginner videos, last lecture notes, practical guides,
Yeah.
works,
To distill it down,
so you can grasp the essentials quickly.
that's the plan.
Okay, so what's on the agenda? We're hitting the big ones. Supervised versus unsupervised learning.
Yep.
Then regression versus classification. Like, what kinds of answers can we get?
Different questions, different tools.
We'll look at how models actually learn and, importantly, how we tell if they're any good.
Evaluation, yeah. Crucial.
Plus that tricky issue of overfitting.
Ah, yes, overfitting. Always a hot topic. And how to tackle it. And we'll wrap up with a look at a real foundational technique, linear regression.
Sounds good.
All right, let's kick off with that first big split. Supervised versus unsupervised learning. What's the main difference there?
Well, the core distinction, really, it's about the data you feed the model.
Okay.
In supervised learning, the data comes with labels. It's like teaching a kid flashcards. This is a cat. This is a dog.
So input and the right answer are paired up.
Exactly. The model learns from those input-output pairs. Think email spam filters. They learn from emails already marked spam or not spam.
Learning with a supervisor, basically, with the answers provided.
You got it. It has a guide.
So what about unsupervised then? Sounds like the model's on its own.
Pretty much, yeah. In unsupervised learning, the data is unlabeled. No right answers are given during training.
Okay. So what does it do?
Its job is to find hidden structure, patterns, groups, whatever emerges from the data itself. No explicit guidance.
Like an explorer mapping unknown territory.
That's a great analogy.
Yeah.
Finding the key features without a map.
Okay, got it. Supervised, labeled data needs answers. Unsupervised, unlabeled data finds its own patterns. Makes sense. Now let's talk regression and classification. These sound like different types of problems ML can solve.
They are. The difference is really about the kind of output you're trying to predict.
Okay.
Regression is what you use when you want to predict a continuous numerical value, something on a scale.
Right.
Okay, think of Lucy, the fitness coach example. She might want to predict how much weight a client will lose. That prediction, say, 5 pounds, 8.2 pounds. It's a number on a continuous scale based on things like calorie intake, workout time.
Right, a specific quantity. Got it. And classification.
Classification is different. It's about predicting a category or a class label. Is it A or B, or maybe A, B, or C?
Discrete options.
Exactly. Take that movie example. You have features like length, genre, maybe genres coded, like 0 for action, 1 for romance. The classification model could predict if a viewer will like the movie, let's say label 1, or dislike it, label 0. The output is one of those specific categories.
Okay, clear. Regression predicts a number, classification predicts a category. Simple enough. But how do these models learn? It still feels a bit like, magic.
Less magic, more process. It's pretty systematic, actually. Usually involves a few key steps.
Like what?
First, you got to pick your algorithm, your tool. Linear regression, decision trees, neural networks, lots of options. Depends on the problem.
Choose the right tool for the job. Step 1.
Then you feed it data. This is the trading part. The algorithm crunches through the data, looking for those patterns, those relationships between the inputs and, well, the outputs if it's supervised.
Okay, it learns the connections.
Right. And once it's trained, you can give it new, unseen data, and it'll make predictions based on what it learned.
And you mentioned libraries like scikit-learn in Python. They help here.
Massively, yeah. These libraries have pre-built versions of tons of algorithms, so you don't have to code, say, a decision tree from scratch every time.
That makes it way more accessible.
Definitely.
Yeah.
You can focus more on applying the models and understanding the results.
Okay. Now, you also stressed splitting the data. Training set, testing set.
Sure.
Why is that so critical?
Absolutely vital. It's all about generalization. You want a model that works on new data, not just the data it already saw.
Right.
So we typically split our data, a chunk for training the model, the training set, and another chunk kept totally separate the testing set. Sometimes a validation set too, for tuning.
So the model never sees the test set during training?
Never. We train on the training data, then we evaluate how well it does on the unseen test data. That performs on the test set. That's the real measure.
It's like the final exam.
Exactly. It shows if the model actually learned the underlying patterns or just memorized the training examples.
Makes sense. And for regression, you mentioned error and residuals.
Yeah. Simple idea, really. The model makes a prediction, say, predicts a house price. We compare that prediction to the actual price.
The difference.
That difference is the error, or residual. And the goal, for many regression algorithms anyway, is to find the model that makes these errors as small as possible overall, minimizing the mistakes during training.
Okay, find the best fit by minimizing those differences. Got it. So once we have a trained model, how do we know if it's actually good? How do we measure performance?
Right. Evaluation is key. You need metrics, numbers that tell you how well the model is doing, how large its errors are.
And the metrics depend on the problem.
Exactly. Use different metrics for regression than for classification, or for unsupervised tasks, like
Right.
different scorecards for different games.
Okay. And when we start evaluating, you said we run into this bias-variance trade-off. Sounds important.
Fundamental, yeah. It's this constant tension when you're building models, bias and variance.
Okay, refresh my memory. Biases.
Bias is basically the model's inherent error, stemming from its simplifying assumptions. It's the model's inability to capture the true complexity in the data. Simpler models, usually higher bias, they might miss the nuances.
Okay. And variance?
Variance is about the model's sensitivity to the specific training data it saw. How much would the model change if you trained it on a different subset of data? High variance means the model is unstable.
So a complex model might have low bias but high variance.
Often, yes.
Yeah.
A very flexible model can fit the training data really well, maybe too well, capturing noise. That leads to high variance. It might perform great on the training set, but poorly on the test set because it learned the quirks of the training data.
Ah, I see. So high bias. Too simple, misses the pattern. High variance, too complex, learns the noise, doesn't generalize.
You've got it. And the trade-off is, as you make a model more complex to reduce bias, you often increase variance.
And vice versa. If you simplify it to reduce variance, bias might go up.
Exactly. It's a balancing act. Finding that sweet spot, that optimal complexity to get good performance on new data. That's the goal. Minimizing the total error, which involves both bias and variance.
Which leads us perfectly into overfitting and underfitting. These are outcomes of not getting that balance right.
Precisely. They're the two extremes of that trade-off. Overfitting is what happens when the model learns the training data too well.
Including the noise and random fluctuations.
Right. So it looks amazing on the training data, low error, but bombs on the test data, high error. It's memorized, not learned. Classic high variance, low bias situation.
Like that student who memorizes the textbook answers but can't solve new problems.
Perfect analogy.
Yep.
And underfitting. Underfitting's the opposite. The model's too simple. It fails to capture the underlying patterns, even in the training data.
So it performs poorly everywhere.
Pretty much. High training error, high test error. It's got high bias, probably low variance, but it's just not powerful enough for the task. Like trying to fit a straight line to data that clearly follows a curve.
Okay, so both are bad. Both mean the model won't generalize well. And you said overfitting is a really common problem to watch out for.
Oh, yeah. It's a constant battle in practice. Recognizing it, preventing it. That's a huge part of doing machine learning well. Comes up in interviews all the time.
So how do we fight overfitting? You mentioned regularization and ensemble methods.
Right. Regularization, briefly, is about adding a penalty to the model's complexity during training. It sort of discourages the model from getting too complex, trying to keep the parameters in check, helps generalization.
Okay, penalizing complexity.
Yeah.
And ensemble methods, combining models.
Exactly. The idea is, instead of relying on one model, you build multiple models and combine their predictions. Wisdom of the crowd. Kinda.
Interesting.
How does that work? You mentioned bagging.
Bagging stands for bootstrap aggregating. It's a popular one.
Bootstrap aggregating. Okay, break that down.
You take your original training data, then you create many new training sets by sampling from the original data with replacement. With replacement, meaning some data points might get picked multiple times, others not at all.
Exactly. So each new training set is slightly different. Then you train the same type of model, like a decision tree, independently on each of these new data sets.
So you end up with lots of slightly different models.
Right. Each one learns slightly different things, has slightly different biases. Then, to get your final prediction, you aggregate them. For regression, you average their predictions. For classification, you take a majority vote.
Averaging out the errors in a way.
Essentially, yeah. The key benefit is that it reduces the variance of the final prediction. Especially good for models that are inherently unstable, like deep decision trees, which can vary a lot with small data changes.
So, like Lucy the fitness coach predicting weight loss, using bag trees might give a more stable prediction than just one tree.
Could definitely help, yes. Make the prediction less sensitive to the specific clients she happened to use for training. It's used a lot. Healthcare, finance fraud detection, environmental modeling.
Okay, bagging makes sense. Then you mentioned random forests as an improvement on bag trees. What's the extra twist?
It's a clever twist, actually. Random forests are built on the same idea, multiple trees trained on bootstrap samples. But there's one key difference.
Which is?
When each individual tree is being built, at every step where it needs to decide how to split the data, it doesn't consider all the available features. It only considers a random subset of the features for making that split.
Whoa, okay. So not only different data samples for each tree, but also different feature options at each split point within the tree. Why do that?
It adds another layer of randomness that helps to decorrelate the trees even more.
Decorrelate, make them less similar to each other.
Exactly. See, if you have one or two really strong predictor features in standard bagging, most trees might end up relying heavily on those same strong features, especially near the top of the tree. They become quite similar.
Ah, I see.
By forcing each split to consider only a random subset of features, random forests ensure that even strong predictors aren't always chosen. It encourages more diversity among the trees.
And that diversity is good.
Very good. It usually leads to a further reduction in variance and often improves the overall accuracy, especially when you have many correlated predictors. That multicollinearity issue we might touch on later.
Okay, so random forests bagging plus random feature subsets at splits. More randomness, less correlation between trees, often better performance.
That's the essence of it.
Now, what about boosting? You mentioned gradient boosting machines or GBMs. How's that different from bagging or random forests?
Boosting takes a completely different approach. Instead of building models independently and in parallel.
Like bagging and random forests do.
Right. Boosting builds models sequentially. Each new model tries to fix the mistakes made by the models that came before it.
Iterative improvement. Learning from past errors.
Exactly. Think about the house price prediction again. A GBM might start with a simple model. It makes some predictions. Some are good, some are way off. The next model in the sequence focuses specifically on the houses where the previous model had the biggest errors. It tries hard to correct those specific mistakes.
So it targets the difficult cases.
Precisely. This sequential process continues to build a model, identify errors, build the next model focusing on those errors, and so on. Each model adds a bit more predictive power, correcting the residuals of the ensemble built so far.
And GBM is a specific type of boosting.
Yes. Gradient boosting is a very powerful and popular implementation. It uses gradient descent optimization to figure out how each new model should best correct the previous errors. Often gives really high accuracy, sometimes better than other methods like AdaBoost. You'd evaluate it with metrics like mean squared error, visualize predictions versus actuals, the usual process.
Wow, that sequential error correction sounds really powerful. Okay, let's pivot now to that other foundational technique. Linear regression. Feels like going back to basics almost.
It is fundamental, yeah.
Yeah.
But super important. It's about modeling a linear relationship between variables.
Linear meaning a straight line.
In the simplest case, yes. Simple linear regression. One input variable, x, one output variable, y. We model it as y is plus b or x plus na.
Okay, let's break that down. Y is what we predict.
Right, the dependent variable. X is our input, the independent variable.
And beta 0.
Beta 0 is the intercept where the line crosses the y-axis when x is 0. Beta 1 is the slope, how much y changes for 1 unit increase in x.
So beta tells you the strength and direction of the relationship.
Exactly. And the epsilon, that's the error term. It captures everything. The linear model doesn't explain random noise, other factors we didn't include.
Like your class size example. Average test score predicted by class size.
Perfect example. Test score of test plus class size plus VETO. If a VO is negative, it means bigger classes are associated with lower scores, on average. The goal is to estimate beaters and beta and beater from our data.
How do we estimate them? Find the best line.
The most common way is called ordinary least squares, or OLS.
OLS. Okay.
The idea is simple. Find the line that minimizes the sum of the squared vertical distances between each actual data point and the line itself.
Those are the residuals again?
Yep. Square them so positive and negative errors don't cancel out and larger errors are penalized more. Add them all up and find the line, the arrow, that makes this sum as small as possible.
Minimizing the sum of squared errors. Got it. That's for one input variable. What if we have multiple inputs affecting the output?
Then we move to multiple linear regression. The equation just extends. Y epsilon plus x euros plus scarm plus x euros plus scarm.
So each input variable, x zeros, etc., gets its own coefficient, a Corin constant.
Correct. And the interpretation of, say, is now the change in y for a 1-unit change in x zero, holding all other x variables constant.
The holding others constant part is key. Isolating the effect of each variable.
Crucial for interpretation. And we still use OLS, typically, to estimate all these betas simultaneously, minimizing the sum of squared residuals in this higher dimensional space.
And implementation. Still libraries like scikit-learn.
Yep, scikit-learn is great for prediction with linear regression, but if you want more statistical detail significance tests, confidence intervals for those betas. The stats models library in Python is often preferred.
Why stats models for that?
It gives you more output focused on statistical inference, like those p-values for each coefficient.
Right, the p-value tells you if a variable's effect is statistically significant, unlikely to be just random chance.
Exactly. Typically, a p-value less than 0.05 is considered statistically significant, suggesting the variable has a real association with the outcome in the context of the model.
Let's use that California housing example again. We want to predict median house value using income, house age, average rooms. We'd fit a multiple linear regression model. Using stats models, we'd get coefficients for income, age, rooms, etc., and their p-values.
Correct. So you could see, for instance, that median income likely has a significant positive effect, higher income, higher value, while maybe average rooms also has a significant effect, controlling for income and age.
Super useful for understanding what drives the price. What about non-numerical features like ocean proximity in that data set? Categories like inland, near ocean. How does linear regression handle those?
Great question. We can't just plug inland into the equation. We need to convert categories into numbers using dummy variables.
Dummy variables.
Yeah. For a category like ocean proximity with, say, 5 levels, near bay, 1H ocean, inland, near ocean, island, you pick one level as a reference or baseline. Let's say near ocean is our baseline.
Okay.
Then you create binary 0 or 1 dummy variables for the other levels. So you'd have a variable is near bay, 1 if true, 0 if false, is inland, 1 if true, 0 if false, etc. You wouldn't create one for the baseline category.
Why not for the baseline?
To avoid perfect multicollinearity, making one variable perfectly predictable from the others. So if a house is inland, I inland is 1, and all other dummies are 0. If it's near the ocean, the baseline, all the dummies are 0.
Okay. So how do we interpret the coefficients for these dummies? Like a coefficient for Iceland.
That coefficient tells you the estimated average difference in median house value between houses that are inland and houses that are near ocean, the baseline, holding all other variables constant. If the coefficient is negative, it suggests inland houses are, on average, cheaper than near ocean houses, controlling for income, age, etc.
Clever way to incorporate categories. One last thing on linear regression, any major pitfalls to watch out for?
A big one is multicollinearity, which we hinted at. That's when your independent variables are highly correlated with each other.
Like maybe average rooms and average bedrooms are highly correlated.
Exactly. If you include both in the model, it becomes difficult for the model to separate out their individual effects. The coefficient estimates can become unstable, variances inflate, and interpretation gets messy.
So check for correlations between predictors.
Definitely. Look at a correlation matrix. If you see very high correlations, like 0.8 or 0.9, you might need to address it, maybe remove one of the correlated variables, combine them somehow, or use techniques like ridge regression, which are designed to handle it, making sure your model is reliable and interpretable.
Okay, that's a really helpful deep dive into linear regression, too. Wow, we've covered a ton of ground today.
We really have, from supervised versus unsupervised, regression versus classification.
Model training, evaluation, that crucial bias variance trade-off.
Overfitting, underfitting, and how ensembles like bagging and random forests help.
And finishing with the nuts and bolts of linear regression, including OLS and dummy variables.
It's a solid foundation.
Absolutely. Getting a grip on these core ideas feels, well, essential for anyone wanting to really get into machine learning or data science. It connects so many dots.
It really does. And seeing how these apply is key.
Makes me want to actually fire up Python and try out scikit-learn, pandas, stats models.
Yeah.
Get hands-on.
That's definitely the best next step. Applying it cements the understanding. No substitute for doing.
Well, this has been incredibly insightful, thanks. And just to leave everyone with something to think about. Now that you have this introduction, this glimpse into these fundamental machine learning ideas, Think about this. The ability of machines to learn from data isn't just another tech trend. It feels like a real shift in how we approach solving problems, how we discover knowledge,
Yeah.
pretty much everywhere. So the question is, what new possibilities does this unlock for you in your world, your areas of interest?